everyone. I want us to look at that example from up above a little bit in more detail, where you thought about the area of a square as a function of its side length. So for instance, if you're imagining a square that has a side length of 1 inch, so you're imagining just a 1 by 1 square. Well, certainly if you have a 1 by 1 square, well, the area for that square is just 1 square inch. But if you're now imagining, let's say, a 2 by 2 square, so 2 inches by 2 inches, well, then the area of that particular square is now 4 square inches. And maybe one more, just to make sure we're understanding. If you're imagining, let's say, a 4 by 4, so it's 4 inches by 4 inches, well, then the area of that square would be 16 square inches. And so that was the previous example where you just thought about the area as a function of its side length for a square. It is simply that whatever that side length is times itself, also known as side length squared. Okay, well, what I want us to look at now are the changes in the area as it relates to the changes in the side length. So for instance, if we start with a 1 by 1, imagine that we go from a 1 by 1 to a 2 by 2. So we've officially increased the side length by 1 inch. We've increased the change in the side length. We've increased the side length by 1 inch. Well, if we do that, certainly the area goes up as well. And the area would go up by the change in the area. It would go up by 3 square inches. And if we do that again, let's say we increase the side length from 2 to 3. So again, I've just added 1 extra inch to each side. But if we do that, the area also increases, but this time it increases by 5 square inches. One more time, if we increase from 3 to 4 inches, so again, we've just added 1 inch to each side. Well, this time the area would go up, but it would go up by 7 square inches. So piggybacking off of a previous unit, we can look at these values and say right away, this table is not linear. This relationship is not linear. It does not have a constant rate of change. This area function does not have a constant rate of change. All of these values are different. 1, 3, 5, 7, 9. Those are not all the same number. That is not a constant range or a constant rate of change, period. But even though it doesn't have a constant rate, can we also acknowledge, though, even though these numbers aren't all constant, they aren't all the same, they do have a pattern, don't they? 1, 3, 5, 7, 9, 11. Even though they're not all the same number, they do have a pattern. Each one of those areas, the changes in areas, goes up by 2 additional square inches. And so this table, even though the area itself does not have a constant rate, the changes in those areas do have a constant rate. And that's what's cool about quadratics. The same way that we were able to, analyze the changes back in our first unit, and by looking at those changes, we can say, nope, this table is definitely not linear, does not have a constant rate. Okay, cool, it does not, you're right. But now, if you analyze a table's data, and it doesn't have a constant rate, no, it does not, but the rate of change does have a constant pattern, like these rates of change had a constant pattern or a constant rate of change, that, friends, is what makes it quadratic. And you'll learn more about this in, maybe your next class. For now, we just kind of appreciate the relationship that exists in quadratic models. And we kind of use that as a stepping stone to understand these are not linear. They are increasing by a little bit more each time, but the little bit more each time that they increase by is indeed constant. So that's kind of cool. And that's definitely a characteristic of quadratics. So thank you for your time, and let's go dig into some quadratics some more, shall we? Thank you.